This is work on structured learning and graphical models. It's joint work with Pushmeet, Kohli, Dhruv Batra, and my advisor, Rob Rutenbar. And so to introduce the problem, the idea here is we want to learn a mapping, where you have an input, like an image here, and the output is this fixed size tuple, where each element in the tuple is a structured label, and where the elements in the tuple are what we call diverse with respect to each other. So what I mean by diverse here is that we will have some measure of what we call diversity, some sort of a distance measure between structured labels. So for instance, in this binary labeling application here, a possible distance would be the Hamming distance, right? So how many pixels take a different label between two labels. And so, for instance, in that first pair example, we could say that those two labels are not very diverse. They almost look the same. However, the second pair there is more diverse because, the Hamming distance is higher. So sometimes it's just easier to speak of relative diversity. Something is more diverse than the other. And again, our task is outputting a fixed tuple of diverse structured labels. So just to motivate the talk real quickly, essentially we want multiple predictions whenever there's some form of uncertainty, so many modes or ambiguities in the task. Also, because of limitations in our model inference or learning, multiple predictions are very useful. They're also useful when you have cascaded architectures. And there's many forms of cascaded architectures. And people have also talked about just looking at the topography of your distribution. By having multiple solutions, you can do statistical analysis on solutions and characterize their energy function, things like that. Now, the idea of diversity, why is it useful? What we have observed is that diversity essentially maximizes your information gain. It helps you identify salient aspects of your output space. So by enforcing diversity, we're able to cover more interesting or important cases, and we're able to avoid wasting time in redundant configurations or solutions. Having a diverse tuple of predictions or a diverse M-best list of predictions also helps us summarize the configuration space efficiently and do things like approximate minimum base risk decoding. So a few illustrative examples. A couple of years ago, we worked on this application where we have as input a video, and we wanted to track human body poses across the video. And so one thing we could do there is, for every frame, produce a set of diverse human body pose detections, right? And then we would use a temporal model across the frames to smooth out a track, right, of human body configurations in video. That worked quite well. Another application could be in interactive segmentation, where the user scribbles on an image and you want to segment essentially foreground from background. Well, if the user doesn't give you unambiguous scribbles, then you could do better by producing a set of diverse outputs and then letting the user choose what he likes best. So in related work, some people have also used an diverse M-best list of parses for translation. So by having diverse parses, translation accuracy is improved. In upcoming CVPR work, we're using diverse predictions to relocalize a camera. So just to motivate these ideas. So current methods, most often to generate multiple solutions, what people do is they take a standard graphical model, which I call a single output model. And they compound it with something like sampling or MBES map inference or search, which, by the way, all of these approaches are expensive, right? Or variational inference is also another way to do this, but it will introduce more inaccuracies in your model, which again is what we're trying to avoid. And one more problem with all of these approaches is that normally you train these models to produce single outputs, but then you're using them to produce multiple outputs, and that seems questionable. Now, current methods to produce diverse outputs. Normally, if you already have this previous methods to produce many outputs, what you could do is take a large list of many outputs and filter it such that what you get is a set of results that are diverse with respect to each other, right? The problem with this is that you first need to generate very many outputs with a computationally expensive method, and then you have to evaluate them for diversity. In previous work called the diverse MBES map method, we showed how to do that a little more efficiently. However, that method is still sequential. So essentially, you produce the most likely solution, and then your second best solution, you penalize it for lack of diversity, using a linear term on a Hamming distance, say. And you do that sequentially with respect to all your previous solutions. Again, this is sequential and it's expensive, and trained test procedures are a little different. Structured DPPs are another method that has been proposed. A couple issues with it is that it allows for low tree width only, and it's also sequential. It's a sampling inference in these methods. In previous work, we also, here we were also learning to produce tuples, and actually in this work we build upon this multiple choice learning idea, and so I'll explain this in more detail later. So in this work, what we want is to achieve a model and a learning method for generating these multiple outputs with an explicit control on diversity, explicit preference on diversity. We want it to be efficient at inference at test time. We want to have consistent train and test procedures, and we want to allow for as many structured output spaces as possible. So again, the question is, can we learn to predict tuples like this, which I denote with this uppercase Y hat I. And the answer to this question is yes, this is possible. And one way to do so is by using this min set loss, which we're working with since 2 years ago. That what this loss says is my output, my structured tuple prediction will be penalized only for the best element according to the task loss in this tuple, right? So for example, in this segmentation task, if I have one good solution, doesn't matter what else I have there, my penalty will be low, right? We call this the min set loss, and it has a few nice properties to it. First property is that it does not forbid diversity, right? My predictor can be very diverse, and it's not penalized for it. It also applies to standard data sets, so meaning I don't need tuple labels in my data to train with this loss. I can have a standard single label data set. However, again, the problem we're addressing here is that we don't have a preference or an explicit control for diversity, and this is just potentially wasteful, right? I may be wasting one of my slots in my output tuple by not being diverse enough. So what we do in this work is compound this bin set loss with a penalty for lack of diversity. And we introduce it through this trade-off parameter alpha, which is a sort of knob on diversity. So I can turn that up if I want things to be more diverse. And the second key idea here is that we will only use this penalty at train time. And so just very quickly preliminaries, because what we're doing is very similar to structured learning for SVMs. So we want to learn mappings, or in structural SVMs, the render case, we want to learn mappings from an input space like X, which are images or English sentences, to a k-variate structured output space like image segmentations or Chinese translations of English sentences. We assume this is a linear mapping which is parametrized by W and uses an arbitrary feature map, which is another mapping from input-output pairs to a d-dimensional real vector, right? We also assume we're giving a taskless function that measures for a pair of predictions, how bad one is with respect to the other. So if yi is ground truth and y hat I is my prediction, that will give me a penalty for predicting something that's not quite right. And so the idea in training structural SVMs is to minimize the expected risk, which, since we don't have access to P, we use data sample as a proxy and minimize the empirical risk. So in empirical risk minimization, we want to find this W vector of parameters such that the loss on the data set is minimized. Now, this taskless is normally non-convex in W, and so people use a surrogate loss such as the structured hinge loss with margin rescaling. Right, so the structural SVM learning formulation is going to look like this, where we have a summation over the hinge losses on my data sample, and we have a regularizer. And this is just a quadratic program that I can solve using a cutting plane or a stochastic subgradient method. Okay, so if I lost you, here's when I go back to my talk, to the actual work we're doing here. So in this work, we want to learn a mapping from, again, an input space X, but now to an M-tuple of k-variate structured outputs. We again assume that the mapping is linear, parameterized by this uppercase W vector. Now, for efficient inference in this talk, we will assume every element in this output tuple is predicted independently. So I have a subset of weights that pertain to one and only one element in my output tuple, as in equation 14. Again, I will train this mapping using the min set loss, and I will penalize for lack of diversity. This is, down there is an example of a penalty for lack of diversity. So the intuition say, for all pairs of labels in my output tuple, I have a measure of diversity such as the Hamming distance, which is negated, because I want to penalize for lack of diversity. And then I will aggregate all measures for all pairs using something as average or minimum. So the learning formulation, again, very similar to structural SVMs, is just find this vector W that minimizes the diversified risk on my data sample. And what I will do next is specify what the block coordinates are, which non-surprisingly will be the parameters associated with each element in my output tuple. However, this optimization is not as simple because the predictors at train time are coupled by this loss, especially the diversity penalty component to it. And so we have to do some not as trivial stuff. So for that discussion, to describe my coordinate and my coordinate update, I need a few more definitions. And I'm going to have to speed up. So essentially, I will use these definitions to select out and fix most of my output elements and only vary one of them. So equation 19 says output tuple when I remove one element, the mth element. Equation 20 says output tuple when I replace the mth element with something else. So what I can do with this is write a truncated form for my diversified loss that says if the mth element, the one I'm focusing on right now, achieves the min loss, then I'm on this linear part of this truncated loss. And if not, then the rest of the output tuple will fix the taskless component to my loss. And so by rewriting the the learning formulation with this, I'm going to get to this equation 22, where now I minimize only with respect to one, the weights associated with one element in my output tuple. So next I'm going to separate the two cases in this truncated form. And for that I also need information that tells me which of the two cases applies to a given example. So now with that information I can rewrite 22 as 26. And again, this is just rewriting so far. And finally, I'm going to use surrogate losses as in structural SVMs, and I'm going to use a regularizer. Again, these surrogates are hinge-like, and this is again a QP, so I can solve this with cutting plane or stochastic subgradient. Okay, so I'm going to go real quick to the results. We had two applications in the paper, foreground-background segmentation and protein side chain prediction. And we tried two baselines, the diverse MBES map algorithm and the multiple choice learning baseline, which corresponds to our approach here without the diversity penalty. So the first task, again, is just binary segmentation of images. We have a pairwise attractive MRF. And we split the results into two sets. So what we do is that we compute superpixels to make things a little more efficient, to have fewer things to label. And in the first set of experiments, we had very coarse superpixels, as shown above. And for the regular task, we wanted to have like finer superpixels. The pairwise loss we used, so the task loss we used is the Hamming distance, normalized Hamming. The evaluation metric I will be reporting is this min set loss, so the loss for the best element in my output tuple. And the diversity augment I'm using for penalizing lack of diversity during training is this mean over the Hamming distances of all pairs in the output tuple. So every time I show a plot, lower is better. And here is the first plot. So this first plot is a little loaded, so I'm going to take some time to explain it. We have train error and test error. So train is my circles, and test is the stars. And I have three colors where black corresponds to high regularization strength. And then green is the other end, so very low regularization. So in the black, what we see is the x-axis, we are varying this alpha, so going from no diversity penalty to more diversity penalty, and again, lower is better. So what we see here is that for high regularization, for the black plots, alpha is actually helping both during train and during test. So I get better train and test performance by increasing diversity. However, at high regularization, what's happening is that the circles, so train performance is more so modulated. Alpha modulates the fit to train, but then the stars, at test time, what I see is that performance is sustained or improved, right? And here gains are marginal because the task is kind of simple with the coarse and superpixels. So trends as we increase the size of the tuple. So again, the diversity component helps throughout all M. And we see that for very high M, again, performance is better for both train and test. And with regular superpixels, we see similar trends. Again, alpha modulates fit to train and leads to increased performance at test time. In comparison against baselines, and this is my last slide. So first, both approaches, MCL and diverse MCL, in our approach here, which we call diverse MCL, they both learn to produce these diverse outputs. And so they're better than diverse MBES map. And then the approach we propose here is better than the approach without the diversity penalty. So that's it for the talk. Thank you.
Okay, so we have time for some questions. Looks like there's a question over there. So the min set loss seems a bit strange in the sense that if one structured output fits the data well, I can then pick really far away structured outputs, but that are very diverse. So wouldn't a max set loss be better so that everything fits the data and I have a diverse set of outputs?
I mean, I think the way we think about it is that we want one output to explain every data sample. So we want one of the elements to explain every data sample, and then we allow different samples to be explained by different elements in the tuple. I don't have a lot of experience with the max version of the loss, but I would think it does the opposite, right? It would penalize for diversity, so it will lead to reduced diversity. And again, what we're seeing is that diversity is helping quite a bit in applications. But again, I don't have experience with it.
Okay, any other questions? So maybe I can ask kind of an imprecise question. One thing that kind of came up as I was thinking about your talk, you used a very kind of regularized risk-motivated formulation for how to do diverse prediction. But in some sense, in graphical models, let's say you want to take a sample from the posterior of the model, then you want to enforce diversity but still fitting your data. And in some sense, this is at least in the direction of what people want to do with maximum entropy regularization. So is there maybe some connection that you can think of between those two things?
I'm not fully sure I understand the model.
Okay, maybe I'm just being too abstract, but
does it have anything to do with trying to approximate like a very complex distribution with multiple simpler distributions, maybe?
Well, yeah, perhaps. I guess there's a difference in that, in some sense, on the one hand, you want to have constraints that say that you're as uncertain as possible. So then if you would sample from that distribution that's maximizing uncertainty while still fitting your data, then you would have non-zero probability in parts of the space that that would somehow be diverse, I suppose. Maybe that would be the case.